Okay, so my topic today is RDU net. It's a novel AI model that I introduced. We are using it for metal artifact detection in SPCCT. Okay, so what are metal artifacts? First of all, we'll see what computer tomography is. A simple CT is basically where we use X-ray radiations in order to map out the internal structure of our body. And one of the major problems that we've seen with CT scans, especially now when there are a lot of prosthetics and metal implants inside the body, is of blooming artifacts, which we commonly refer to as metal artifacts, because that's the predominant or the main prominent thing that causes these blooming artifacts. So we simply just call them metal artifacts. So the most common types of metal artifacts are beam hardening, scatter, noise, NLPV. These are different kinds of basically artifacts that join together or combine in order to give this kind of outputs. You can see in the first photo the with metal artifacts or with metals, there are a lot of streaking, there's a lot of loss of data that we see when we're dealing with normal conventional CD. This is an example of a normal CD. And this is what an actual scan should look like without the metal artifacts. That's what we're trying to achieve as well. However, we're not using a simple CT or a conventional CT. We are using a photon counting or a spectral CT. The best part about spectral CT is that it gives us a lot more information. It gives us the information for 5 different energy bins at a time. And that's very good for us, especially when we are moving on to further analysis like material decomposition and stuff like that. So currently, the problem that we face is that when we're dealing with spectral photon counting, most of the studies that we found rely on simulations, not on actual data from SPCCT. Secondly, most of these studies basically join all those 5 energy bins or different energy bins together in order to form one image that is free of artifacts. But for further analysis, we need all the data that's been provided to us. Why would we lose data just to remove metal artifacts? So that's what my aim was, in order to create a model that can correct metal artifacts all at once in all 5 energy bins. So that's equipment, that's the Mars photon counting CT or the SPCCT that I was using. It's called Mars Microlab. It gives us, for us, what we use is like 5 energy bins at a time. The QRM phantom, which is because this is a phantom study basically, because our machine can only work right now on mainly on phantoms, and it's a small bore CT. So that's the metal insert. We have metal inserts of aluminum and steel mainly. This is the size and this is the dimensions of it, the metal insert. The acquisition parameters that we use are mentioned here. The tube voltage is 100 NT, tube current is 80. This is basically acquisition parameter that we ourselves formed or we ourselves ended up with that gives us good enough information, the best that we could process at our level. So because SPCC data is very heavy and it's like almost 8.5 million pixels in a single slice. And we're dealing with like 150 to 200 slices per scan. So that's a very big problem in SPCCT. That's the type of data, that's all the data sets that I use. The training data sets for training, that's in the yellow part, there are like 6 different scans with different placements of aluminum and steel inserts as well as different materials inside it as well. Then we have data set for validation, which we use to validate our results, and the last is the data set for simulation. You can see how these data sets were used here. The data sets for training, we took a 50 millimeter scan, 20 and 20. We used 10, we left in the middle so that there are no residual artifacts. We divided it into input images that contain steel and aluminum, and then empty images that basically contain no metal at all. The data set for simulation basically was used to extract the metal attenuation profiles of steel and aluminum, and then we used the empty images from the data sets of our training and the extracted values from simulation, data set for simulation, in order to simulate a data set that we used as a ground truth for our AI model. That these input images and simulated images were fed into an algorithm, which in our case is an RDU net model, and we were getting the results that were evaluated using the validation data set. This is the model. Basically, it uses dense blocks and residual layers in a U-net fashion and a U-net backbone in order to drive the outputs. Basically, the data was too heavy and we could not use normal models, so we made our own that had enough depth in order to basically give us optimal results, but also was not that hectic that we cannot use the data that was 5 by 1300 by 1300 for a single slice. So dense block basically I introduced in order to facilitate as much feature reuse, so that we can reuse features instead of using new ones, and we also increased the depth of the model in order to give optimal results. The residual blocks tackled the problem of vanishing gradients and made sure that our features were not lost during the depth of the network. These are the results, the inputs, the simulated and the outputs. The simulated are basically the base, or the most simply in our stage, it's the control group. This is what we want, and the outputs, as you can see, are much, much better. The inputs are very noisy, it has a lot of streak, a lot of artifacts, but the outputs gave very good results. These were the outputs were compared with the simulated, and so were the inputs, and this is the result of the evaluation matrix, which was SNR. As you can see, the SNR, the blue is the input and the yellow is the output, and you can see how much the SNR increased, just the SNR. The second is the root mean square, which decreased almost to a negligible amount, as you can see in the graphs as well. The structural similarity index, which should be 1. It should be as close to 1 as possible. 1 is the best possible. And as you can see, it increased for all the available inputs and outputs that we have across the board, all 5 energy bins. This is for all 5 energy bins, all three of those evaluation metrics. So as you can see, our results were very good. So we moved on to the next stage, which was material analysis, which also gave very good results to us for both iodine and hydroxyapatite elements. So that's the proposed RDU network, and it gave us very good results. And we are currently trying to use biological data set in order to finish and improve our model. Thank you.